Okay, let's go ahead and take a look at equivalent fractions. So what we have is our number line, which you should all know how to do. And with our number line, what we're going to do is we're first going to start off by showing what 1/2 is. So I take my number line and I partition it into 2 equal parts. And if I have multiple segments, then I can split those segments into 2 equal parts. So this becomes 1/2, and this would be 2/2, obviously, and then 3/2, and 4/2. Well, let's say we want to find an equivalent fraction that would be the same as 1/2. Well, we can do that by partitioning our line segments again. Let's say we want to partition each of our line segments into 3 equal parts. So in this case, we're going to partition this first line segment into 3 parts. This is partitioned into 3 parts, this one, and this one. Well, now when you relate it between 0 and 1, how many partitioned areas do I have now? I've got 1, 2, 3, 4, 5, 6. So now this becomes 1/6. This becomes 2/6. And our next partition is 3/6. So what has happened here is this particular point on the number line is 1/2. But if I partition into smaller parts, it also becomes 3/6, which is an equivalent fraction. And again, remember, they're equivalent because they occupy the same point on a number line. Okay, let's try that again with another number. Let's try 4/3. So if we are going to partition our unit segment into thirds, I make that one partition to 3, do the same thing with the other segment, and now this becomes 1/3, 2/3, 3/3, 4/3, 5/3, and 6/3. Alright, so here is 4/3 right here, and let's say that we partition each of these pieces 5 more times. So I'm going to take this part and partition it 1, 2, 3, 4. That's going to give me 1, 2, 3, 4, 5 partitions. 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So now my partitions, instead of being in thirds, if I look between 0 and 1, I actually have 15. So if I count all these up, this first one would be 1/15. And I'm not going to write all these in, but 1/15, 2, 3, 4. 1/3 would become 5/15. If you move to the next one, this would be 10/15. This would be 15/15. And so 4/3, what we were looking at, is 20/15. So that means if we have 4/3, then an equivalent fraction could be 20/15 if I partitioned it 5 more times. So that brings us to our equivalent fraction theorem. Given 2 fractions, and if we generalize this using our symbols, m over n and k over l. Now what is not listed here is that m, n, k, and l, we have to quantify those. So we're going to call them whole numbers. We're not even going to deal with negatives right now. So these symbols are going to be whole numbers. Suppose there is a non-zero, meaning that it can't be 0, whole number c. So we're going to add another symbol, which is a whole number, so that when you multiply, k is equal to c times m, and l is equal to c times n. If you do that, then m over n is going to be equal to k over l. Why? Because m over n is the same as cm, or c times m, over c times n, which is what we just said here. C times m is equal to k, c times n is equal to l, therefore these two are equivalent. So here's an example. If I have 1/2 and 3/6, well, 1/2 is my m over n, and my constant is going to be 3. So if I multiply both the top and the bottom by 3, I get 3/6. So 1/2 is the same as 3/6. 3/6 is now my k over L. All right, let's take a look at 4/3. If we start with 4/3, my constant that I'm multiplying by, in this case, is 5. So if I multiply the top and the bottom by 5, then I get 20 over 15. Notice that because when I partition, it's almost like division. Although I'm talking about multiplying here, I'm multiplying parts, which are division. So see how that relationship between multiplication and division unfolds. All right, so let's take a look at the converse of that, which is called the cancellation law. So if you have a whole number c, and it divides whole numbers k and l, then KL is k divided by c, and L divided by c, which is going to take me back to m over n, which is equal to k over L. So let's take a look at 3/6. If I divide, so if I take 3/6 and divide it by a whole number, in this case let's say 3, so divide the top and the bottom by 3, then I'm going to get 1 over 2. So 3/6 is the same or equivalent to 1/2. Let's do the same thing with 20/15. That would be 20 over 15. I can divide both top and bottom by 5. And that's going to give me 4/3. So we are back to where we started from. So the cancellation law is just kind of the opposite of the equivalent fraction theorem. Okay, so let's finish up by looking at a proof of this. So by the equivalent fraction theorem, we can say that k over L is the same as c times m over c times n. All right, and by the cancellation law, we can say that c times m over c times n, you can cancel or divide those out and you are left with m over n. Therefore, since these two are the same, c times m and c times n occur in both of these, you can cancel those out and you're left with k over L equals m over n. So let's take a look at that. Our example is 51 over 34. We can write this as 17 times 3 and 17 times 2. All right? Or you can think of it as canceling, and what happens is you end up with 3/2. So therefore 51 over 34 is equivalent to 3/2. Why? Because they occupy the same point on the number line. All right, see you in class.